Thank you very much for the invitation. So yeah, I'm gonna tell you about some of the results that are in these two papers, and let's see, this one. Okay, yes, which are joint project with Claudia Rella, and she will be here next week. So in fact, she will discuss mostly about the physical aspect of the story related to fermionic spectral trace on local P2, while I will mostly concentrate on the resurgence aspect. And in particular, I will discuss what we introduced in this paper here, which are modular resurgent structure. And so to begin with, I will briefly recall something on resurgence, although I will assume that many of us are already familiar with that. And I will mostly focus on the quantum modularity, which probably is not so familiar. And then I will briefly introduce the example of the fermionic spectral trace for local P2, and finally discuss this more general resurgent aspect. Okay. So as I think people working on resurgence, in particular when divergent series arise from perturbation theory, we know that it's very useful because it's a tool that allows us to go beyond perturbation theory. And how do we do that? The main structure we want to understand is what we call what sometimes is called resurgent structure, meaning that if we start with a divergent series, and for my talk they will all be of class Gevrey 1, meaning that the coefficient of the series are growing factorially fast, then we call the resurgent structure the following set of data. So the location of the singularity in the Borel plane. So after you take the Borel transform of this function f, which gives you a germ of analytic function, we know that they have singularity, and that's are the omega. And at each singularity, you also have a Stokes constant and a new germ of analytic function, which is precisely what we say arise or resurge near each singularity. And so some of the very natural way where resurgence, very natural example of resurgent series, in the spirit of new resurgent series arise at the singularity, are the following example. So in the first one, when you have logarithmic singularity at the point omega, then this Borel transform look like the following. So in particular, you have the logarithmic branch cut at omega, and then you see the Stokes constant and a new formal power series. This is really the new information that you can achieve when you look at the analytic continuation, in fact, of this Borel transform. But sometimes, even most simply, you might just find simple pole at the location of the singularity. In that case, the new series is not really a series, it's just a constant S, which is the Stokes constant. And in fact, in my talk today, all the example will be essentially of this very simple form. Okay, and what about instead quantum modular form? So these were introduced by Daguerre, and in the context of Chern-Simon and in the study for quantum invariant or of knots and free manifolds. And so that's one of the first definition he gave. So a quantum modular form of weight k for some group gamma is a function defined over the rational, and such that what is called the cocycle, so a function from gamma times r to c, defined in this way, has better analytic property of f. Now, f is just defined over the rational, so being better in the analytic sense, for instance, means being a real analytic on r minus some point for every gamma in the group. And here you have like an example that I took from the paper of Don, where on the left-hand side you see that the function f, essentially, okay, this is the plot of the real part. You just got this bunch of points and not very clear like in which way they are organized. But if you instead look at the function h defined by the difference, where now gamma is this element in gamma 02, you see that in fact it's much nicer behaved. In fact, it's real analytic, and here you have like, except to the point minus 1/2, which is precisely this minus d on c. So if you have never seen this function before, I think that the two things to keep in mind is that, first of all, they are not even holomorphic, so it's like the weakest possible requirement that you can have in terms of analyticity. But not only that, even like the modularity, they are not really invariant by the action of the group, because somehow what typically would be 0, in fact, is now with this new function h, which is nicer behaved. And that's somehow the weakest possible definition, but in fact, for my talk today, we will encounter something a bit nicer, so some functions which are holomorphic quantum modular form. So first defined on the upper half plane and holomorphic. And now, in the same spirit as the previous definition, being better behaved for this cocycle H would be being analytic on a larger domain. So if before it was just real analytic on the reals minus a point, sorry, here's a typo, now will be analytic on the full complex plane minus and half line. Okay, and and this is yet not the full general definition. In fact, you also have a vector valued quantum modular form, as in the case of the usual modular form. And I will invite you to take a look at Campbell's thesis, because he has a very nice description on that. Okay. And where does this quantum modular form appear? So we already in the paper by Zagier, there were several examples coming both from combinatorics as well as Chern-Simon. In fact, his motivation was really the study of quantum invariance. But so for instance, you have, if you take the modular discriminant of the Dedekind function, that's a quantum modular form. Also, examples are coming from the theory of mass cusp form. For torus knot, for the trefoil, it was already proved by Zagier that the Kashaev invariant of the torus knot is a quantum modular form. And for more general family of torus knot is a more recent paper by Goswami and Osborne. For hyperbolic knot, it's mostly conjectural, and we have numerical evidence in some example, and that's thanks to the work of some people that I listed here. And also for the Kupo-Kammer symbol, that's in Campbell's thesis, another example of a quantum modular form where the cocycle, so the function given by the difference, is in terms of the Fadeev logarithm. And finally, what we have shown with Claudia in the example of local P2, even in topological string, when we, in the context of topological string for non-compact toric threefold, in particular, if you look at the fermionic spectral trace, you will see new quantum modular form also arising in that context. And among these examples, I should mention, so the first and the fourth one are a bit special in a sense. In particular, in the third one, typically you have a vector-valued modular form. And one aspect that I noticed when looking to this example is that from the resurgence point of view, we can try to characterize some of them. And that's somehow the general idea. So I would like to understand if there is a way to characterize quantum modular form, maybe the holomorphic one, using the property of their asymptotic expansion. And in fact, even though these examples were firstly motivated by Chern-Simon, some of the features of the quantum modular form appear also in other contexts and seems kind of related to the resurgent structure of the asymptotic. So I think it's kind of natural as well to describe this function by first looking at the asymptotic expansion, then use the tool of resurgence to characterize which type of resurgent structure appear, and eventually try to claim that this resurgent structure, in fact, is very particular of some quantum modular form. And even though the picture I'm going to present is not is not completed yet, because, for instance, the example of The hyperbolics not, as well as the first example, do not fit in this picture yet. I think it would be interesting to try to understand them in more generality. Okay, and so let me now go to the example of the first fermionic spectral trace for local P2. So this example is quite rich by itself, not only from the geometric point of view, also from the physical perspective, but I will take today the approach again of resurgence, so I will not discuss much both the physical and geometry perspective, but we can discuss maybe later or in the following days if you are interested. So let me just briefly remind that, okay, what is local P2? Is the total space of this canonical bundle. And in the context of mirror symmetry, these are very natural objects to consider because the mirror has this very nice description. In fact, is essentially captured by the elliptic, by a family of elliptic curve, which here is I choose this particular parametrization, and kappa is a moduli in the which parameterize, so is a coordinate in the complex moduli space, parameterizing the complex structure on the mirror. And let me also add that in this example, the complex moduli, in fact, can be realized as the quotient of the upper half plane by this group gamma 1, 3. And in this context, in the framework of the topological string spectral trace correspondence introduced by Grazia Tsuda Marino, they look at the quantization of this curve. So in particular, at of this function here, and the h-bar parameter of the quantization is in fact related to the string coupling constant in this way. And then they look at the Fredholm determinant. So the Fredholm determinant here is the one with respect to the inverse of this operator. And the quantity I'm interested in are the so-called spectral traces. So that you read in the expansion in this parameter k, which is the same here, at k equal to 0. And I didn't mention it, but k equal to 0 corresponds to the orbifold point in the moduli space. And here everything is exact. So this function, this function here is entire in k, in kappa, sorry. Okay, now that I have this function Zn, I would like to study their asymptotic expansion. So in particular, this was already done by Marino and Dacani and Olsorella, in particular for the first fermionic spectral trace, which means n equal to 1. This is like the general expression given by this integral, and this phi b are the Faddeev logarithm. So before, let's say when I consider the quantization, h bar was just real, but in fact this is well defined also for h bar on the cut plane. And what you can, I mean, deforming the contour and like rewriting the integral, in fact it has this very nice expression in terms of Kupo-Kammer symbol. Little b is just a parameter, and in fact I probably should add that q is e to the 2 pi I b square. So, and this b, yes, is just, yeah, perfectly. Where is h bar? Yes, thanks. There is something else missing, which is that 2 pi b square is 3 h bar, sorry. Yeah. Okay, now looking at the asymptotic expansion of this z in the two limit, which corresponds to the weak, this one, the weak and the strong coupling limit for the string, one gets this very, there is something, sorry, I just got here this, this q should, were with a twiddle, sorry. So in this part, That's a typo, and Q tilde is minus 2 pi I over B squared, sorry. Okay. So in particular, in the two limits, like only one of the two block, in fact, contributes. And in particular, you get an asymptotic series which has a rational coefficient and the coefficients are known explicitly in terms of the Bernoulli number and Bernoulli polynomial. And in the other regime, you get, again, a Gevrey-1 series, and the coefficients are completely determined in this way, because you can use somehow the asymptotic of this Pochhammer symbol to get this formula. Okay, and now you take a look, you study the resurgent structure of these two asymptotic series. This was done already by Claudia in her work. And in one case, what you get is that the singularity are this multiple of 4 pi squared over 3. So you just get a tower of singularity in the Borel plane. You can compute the Stokes constant in closed form. So I'm not writing the expression explicitly, but in fact, you know the Stokes constant, and you can rearrange them as coefficient of an L function, which turns out to be this product of a Riemann zeta function and a Dirichlet L series with respect to this character. The S1 after you remove this are rational. And okay, yes. It's similarly in the other limit. So for the psi, you get again a tower of singularity. The Stokes constant can also be rearranged in an L function, which notice has this shift in the S. So here you have the Riemann zeta at S, and here is shifted by 1, and vice versa for the Dirichlet L function L. And I'm not sure if you are familiar with the L function. So these are analytic functions for real part of S bigger than 1. But in fact, you can also consider the analytic continuation in the complex plane. And that's really, for this type of function, in fact, you will see at the level of the analytic continuation how the two L functions related to each other. And that's somehow the general picture that you get, which is what I would like to call a new paradigm of resurgence. So starting from the L function L infinity, now here this plus or minus is just because you have both the positive and the real, the positive and the negative, constant R. Here I'm just parameterizing R from, I'm just writing Rm. You have both positive and negative, and in fact, they are odd, while the Sm are even. Sorry, there is not. But that's not really important. So if you start with the L function, using the inverse Mellins transform, you can define a function f infinity, which is defined on both the upper and the lower half plane. So on the complex plane minus the reals. If you take the asymptotic expansion of this function here, you would get an asymptotic series, and its resurgent property gives you the Stokes constant Sm. Now, you can build again the L function for the Stokes constant Sm. This is what gives you the L0. You can take again the Mellin transform. You get a nice holomorphic function defined on the complex minus the real. You take the limit again. You get a divergent power series. And if you take the resurgence, if you look at the resurgent structure of this series, you have the Stokes constant are the Rm, which are precisely the coefficient of the L function L infinity. So the fact that you can go from the L function and close this cycle is essentially encoded in the functional equation for this 2L function. So in particular, for this example, you have that the two set of Stokes constant, once you write them in terms of L function, are related, and one knows about the other set. And that's also interesting from the point of view of string theory in what we are trying to describe, because remember now that what I call with the tilde are the perturbative series. So these are the two expansions of the first fermionic spectral trace in respectively the strong and the weak coupling regime. And this vertical arrow now is like the synthesis of doing this half cycle. So in particular, it's like what resurgence is telling you. So going vertical is how you reconstruct the non-perturbative information from the formal power series. If you start with this, so the infinity here is the weak coupling regime. You have the perturbative expansion. Through resurgence, you construct, you recover this F0, which in fact is nothing but the generating function of the Stokes constant. And you can think of it as what contains the non-perturbative contribution. Then you go perturbative again, and if going up, you find what contains the non-perturbative correction of the weak coupling. So the 0 is a strong coupling, above you have the weak coupling, and the horizontal error are the perturbative expansion, the vertical error is what you recover through resurgence. And Claudia will be discuss more about this picture, in fact. And in particular, so the function f0 and f infinity, as I was briefly saying, if you define them by taking the Mellin transform, the inverse Mellin transform of the L function I was giving before, they have this very nice description. So you see they are defined on the complex minus the real. They are holomorphic, and they are the generating series of the Stokes constant. And for this type of function, we show that they are holomorphic quantum modular form for the group gamma 1 free. The way you do the proof is almost immediately once you realize that this function can be expressed in terms of the FADEV, of the Pochhammer symbol. So the cocycle, in fact, is the FADEV logarithm as it's kind of expected for this type of example. But what is interesting is, first of all, that you have some description, some modular description of the generating function, which are also what contains the non-perturbative correction in the both regime. And the other interesting aspect is the group gamma 1 free. So that's really related to the geometry of the problem, because remember the moduli space which parameterizes the complex structure of the mirror curve of local P2 is the upper half plane quotient by this group. And in fact, one of the questions which arise in this context is typically, okay, we study the resurgent structure, we get this Stokes constant. Do they have an enumerative geometric interpretation in terms of the geometry of the mirror, so of local P2 in this case? And that's one of the projects we are currently working on with Claudia. Thanks to the fact that we get some modular description of this generating function, we might, we are trying to understand whether these can be related to the generating function of the Gromov-Witten invariant of X, which is nothing but the free energy, in fact, on the topological string site on X, which are known to be quasi-modular form with respect to the same group. Okay, so that's how quantum modularity somehow appear in this example of local P2. And how does this somehow generalize? And what we are trying to understand is like giving a more general picture of resurgent structure, which reminds the one of local P2, and are also related to quantum modularity. And so that's one of the definition. That's the definition we gave in our paper. So we say that an asymptotic series of type Gevrey-1 has a modular resurgent structure if the following condition holds. And so first of all, we require that the singularity in the Borel plane are in a tower, where A is like what the space all these points. I'm drawing the tower vertically, but in fact, A can be any complex number. The singularity at each point only know about the Stokes constant. So it's like one of the simplest possible version you have, where at each point you only have the Stokes constant. There is no new series which is resurging near the singularity. I'm not specifying which type of singularity, so it can be simple poles. You can have also square root branch cut. That's not, a restriction. And what we require instead is that the Stokes constant can be put in this L function, so that there is an L function which describes the Stokes constant, and it can be analytically continued. So typically it's analytic on some right half plane, but in fact it admits a meromorphic analytic continuation also on the negative reals. So far there is no modularity in fact, but the idea is that we call modular resurgent structure because the idea is that there will be an associated quantum modular form whose asymptotic series has this behavior. And let me also briefly mention that if, for instance, you restrict to the assumption that your divergent power series has not only a modular resurgent structure, but has also simple pole, then the coefficient turn out to be very simple. So you have just factorial growth, and you see here the Stokes constant AK and the position of the singularity at the bottom. So it's very natural somehow. You can build, given if you want an L function, you can build as many as this modular resurgent structure you want. So somehow it's non-empty. And moreover, if you look at the generating function of the Stokes constant using the Mellin transform as I was describing before, you can then, you have somehow a good candidate to be what we'd expect to be quantum modular. And it's what we would like to study through this asymptotic, so we would like to study the asymptotic behavior of this F, because in fact, through the functional equation of the L function, you might have different situations. So sometimes it turns out that this, the asymptotic expansion of this F gives you back F tilde. That's one of the examples we studied in the paper, this mask cusp form with some spectral parameter. But in the example of local P2, this, when we were taking the asymptotic of this function, in fact, we were finding someone new, which was the series G tilde. And that also is, it's really known by the functional equation for the L function. But sometimes you can also get a convergent a convergent series. So in fact, you just end up getting the Taylor expansion of this function, of this F. And all these behavior are kind of encoded in the functional equation of the L function. But only in the first two cases, we would expect to have quantum modular form. In the last case, I would rather expect to have something modular rather than quantum modular. And in this setting, now the conjecture, as I was briefly mentioning, is that if you start now, if you consider a Q series, holomorphic and defined on the upper half plane, was asymptotic expansion, in fact I should say asymptotic series because somehow in the expansion you have some extra term. If this asymptotic series has a modular resurgent structure, then F is an holomorphic quantum modular form for some subgroup of SL to Z and for some weight K as well. That's a bit general somehow, and in particular because I'm not characterizing the L function. So as I was saying in the previous slide, depending on the L function, I mean, I will not expect that for all L function, which encodes the Stokes constant, you get something quantum modular. But in the exam, so maybe it's a bit more general, or somehow we have to specify something more in order to be able to prove the conjecture. But in the example of local P2, now I'm rewriting it in a slightly different notation. So the generating function, the F0 and F infinity that I was writing before as generating of the Stokes constant can be realized as this Pochhammer symbol. And their asymptotic series are of the form I was briefly describing before. So you only have simple poles. Here, this is the factorial growth on both limit. The Stokes constant in both regime appear. Is there an N miss? Ah, oh, here, yes, this is missing an M, sorry, yes. Yeah, here, in fact, now there is no anymore the H bar that was before, and even the tau. I just rewriting everything in terms of this Y, because Y is the natural modular coordinate for the group gamma 1 free, in fact. Is there? No, in general, no. In fact, I mean, okay, in this example, even at the beginning when we were trying to understand what was the natural thing to be quantum modular, we had a different like tentative, and it wasn't clear whether we would get for the full modular group or rather for a subgroup. And then thinking more about the geometry and the fact that there is a natural subgroup in the project, we understood which one was the function, and in fact, which one was the modular coordinate to consider. But I don't have a recipe in general to prescribe it. It could be related to the L function. I mean, okay, that's be the L function somehow should help us understanding it. But yeah, I don't have an algorithm so far. If take instead of the log, you mean? Huh? Oh yeah, I think it became much like convoluted somehow, because then the Stokes constant get all mixed. Okay, that's yeah. Yeah, I guess so, but no, not that I know. In fact, okay, I mean, for us, it was much more natural to work with the log version because we have this nice description in terms of the L function. If we take the exponential and we do the resurgence and so on, we got something a bit more complicated, and so we weren't sure about how to express it in terms of L function. But maybe, yeah, it should be interesting somehow. Maybe we should check more carefully. And other example also appear like in this, when you study, these sigma and sigma star series are arising combinatorics. So they go back to some work of Andrews, Dyson, and Nixon. They were studied by Harry Cohen, which in fact prove there is an L function for the coefficient of this series, which has an analytic continuation. Daguerre showed that these are related to quantum modular form, and with Maxime we are trying to understand the resurgence property of this function. In fact, it's conjectural, and we have like numerical evidence, but somehow I'm still trying to find the analytic proof. And another example, which is in the paper with Claudia, comes from this theory of mask cusp form. And here I'm just writing one of the expression they have. So this function here is in fact modular. These are the Bessel function, an are some coefficient, and then you have real and imaginary part. And something similar also appeared yesterday in one of the talk. And how the quantum modular, I mean, so this is modular. The quantum modular form will be the generating function of this constant. Here, an are just some coefficient again of an L function, if you like. I mean, for a half. Yeah, the, 1/4, sorry. Yeah, the spectral parameter 1/2 should corresponds to 1/4. The eigenvalue is 1/4 for the hyperbolic Laplacian. Mm, it's not, no, I don't think so. I mean, this one, okay, like not this one because I'm not specifying AN, but if you replace the AN in the example of sigma and sigma star with the coefficient of the series, then it's modular for gamma 02. I mean, it's invariant for gamma 02. What you have is that this, so if you take psi to psi plus 1, this is u0 psi, and then you have to take the conjugate. And instead is invariant by the shift by the t. And one of maybe the last thing I'm gonna say, it's also a remark about summability, which I haven't discussed so far, but in fact it's part of the conjecture we have with Claudia. And I think it's also quite natural in the context of quantum modular form. What is the point here? Okay, we still have our divergent series F tilde, and with the tower of singularity as before. And now we can try to understand whether we can, in fact, reconstruct the original F using some suitable summability, resummation technique. And in this case, the median resummation is the one that works. I mean, in the example that we have, at least that's the case. And this median resummation is simply taken, is defined by taking the average between the two Laplace transform in the right and in the left direction. So you just move just slightly to the right and to the left of the tower, and these define an analytic function on the upper half plane or lower half plane. And the conjecture is again that if you have an holomorphic function, so in fact a Q series with asymptotic expansion as a modular resurgent structure, then the median resummation recover F. And when that's the case, if you take the two conjectures together, in fact, what this is telling you is that the median resummation is a quantum modular form. So if you have a function with asymptotic expansion as a modular resurgent structure, then the median resummation is a quantum modular form. And okay, so like in conclusion, let me just mention some of the project or some of the things that I think would be interesting to study. First, like to look at other geometry. So not we have the example of local P2, which is very nice because everything is exact, and so we can in fact understand this L function, and we have the nice description of the Stokes constant, which is typically is not the case when we study this example. So for local F0, there are only numerical results. It will also be interesting to study the next fermionic spectral trace. I just look at n equal to 1, but in fact one can try to go beyond that. And in this paper by Gwen Marino, they in fact studied the second trace for this example, again numerically. There are the fact that there is that we have this quantum modularity for also in the case of the fermionic spectral trace is in a sense another similarity with respect to quantum Chern-Simons. So it would be interesting again to maybe push this construction further, and in particular looking at the other traces to see to exploit more the similarity with quantum Chern-Simons. What is interesting also from a geometric point of view is really the interpretation of the Stokes constant, and as I was discussing before, that's one of the projects we have with Claudia. Thanks to the quantum modularity, we think that that could be a good hint to prove that, in fact, the generating function of the Stokes constant are related to the generating function of the Gromov-Witten invariant of the mirror. There is this strong weak resurgent symmetry that I briefly sketch, and that Claudia will also discuss later, and it would be nice to understand whether this holds also for other Calabi-Yau geometries. And from the point, so this is more or less the part related to the topological string and spectral trace correspondence. while the last part is more about this modular resurgent structure that we are proposing. And in fact, it will be nice if we can get even a much more example in which we can test our conjecture, also to get a better understanding of which shell function we should consider, and yeah, whether we can, in fact, maybe try to prove the conjecture as well. And yeah, so in particular, characterizing the L function, because as I said, if the L function is, for instance, the Riemann zeta or some Dirichlet L function, you will not get something divergent once you take the asymptotic. And so probably that's an instance of modularity rather than quantum modularity. And yeah, so that's all I want to say. Thank you. Yes. They are, yeah, exactly, they are example. And yeah. I think, yes, yeah, in the talk of yesterday of a video, in fact, is also the median resummation is like kind of playing a role when you look at the asymptotic and you try to reconstruct them. So I think it's kind of part of the same setting. Somehow what I'm, in the example I discuss, you get integer weight. In fact, either weight, like the generating function were a function, so weight 0. The sigma star example is weight 1, quantum modular form. When you start looking at knots invariant, then you also get fractional half integer weights. So for instance, the Kontsevich-Zagier series is some weight 1/2 and is related to partial data series. Yeah. Okay, it should be, yes. Yeah. In fact.
Thank you for this.
19, yes.
Were you discussing your general setup? I think I heard you say that these singularities need not be poked, but you could deal with branch points, square root.
Yeah.
How about logarithmic branch?
If you only have the logs times a constant, it's fine. Because in fact, log and simple pole are kind of more or less of the same. In a sense, if I change the definition of my Borel transform, I can go from log to simple poles.
So at the very first slide, you had a dichotomy between logarithms and poles, and you said you were concentrating on one, but you think your universe is big enough to...
Yes, okay, what I was saying at the beginning is that where is it? Somewhere else, here. Here I had the log, but there is this new guy, which if I have a simple pole is essentially not there because it's just the regular part. But if you here replace instead of the simple pole a log and that's it, then it's fine. It's a bit tricky because it's not the real sense of logarithmic singularity. It's just I'm changing the definition of the Borel transform. When you have I mean, even the example I'm discussing now, I didn't mention it, but if you define the Borel transform of Z, let's say, yes, I can take minus n minus 1. So typically, I use this convention for the Borel transform. Now, if you change it with this one, you are morally taking a derivative. So the log became a simple pole. So if you had, if here you had a log, here is a simple pole. So if you have here, if here you see something which is log of zeta, maybe not divided, but sorry, if you have log, and here you have a constant, in this case, it's really the same function will give you s divided by zeta minus omega. It's just, so in a sense it's log, but it's a bit not real log. When I think about log, it's because there is someone next. So there is really the new function here. And again, I mean, I didn't have, I don't have example where I try to understand this picture, I can still try to look at the Stokes constant, also here. Here is somehow natural because you just compute in the residue, it's the only information you have. Above, one could try to say, okay, I have my Stokes constant, I try to build a generating function and see whether they satisfy some nice property, but I never tried myself.
Another quick question, if I may. We've had interesting talk on gamma theory of 2, and now you're on gamma 1 of 3. The final integrals I was talking about last week, the congruent subgroup is gamma 0 of 6.
Okay.
Is there any place for that in your
Oh, yeah, the group can be any discrete subgroup. Yes. So I would be happy to take a look at the example then. No, for okay. I guess yes. If it's genus 1, no. The spectral trait should work for any genus. The spectral, the conjecture is more general. It's not just for genus 1, in my understanding. Yeah. Yes. Sorry, I didn't hear you. No, and congruous group, yes. The L function for the example? Yes, okay. Where do they come from? I mean, that's okay, because I'm not right. If you take a look at how the Stokes constant are defined in terms of this congruent, I mean, now I don't, okay, anyway, it's come from the definition of the SM, and you can realize it using this product, in fact. It's just an arithmetic property somehow of the way you can express the SMS divisor sum function. No, I get the other one. Okay, the functional equation is like this one. Okay, I guess I can erase this. So if this one, okay, I don't remember all the gamma factor, but somehow there is, should be something like that, morally. And then you have L0, and maybe also something in front. This is equal to L infinity of minus S. Yeah. L infinity now is, again, something times some gamma factor, if I'm not mistaken, is minus, should be, and then L infinity of minus S. So you see that on both sides you have the same character. I mean, this, maybe I write the character. This chi32 n is 1, 0, minus 1. If it's 1 modulo 3, okay, is 0 and 2. So if you want, I mean, I don't know if it's readable, but so it's really like the same L function. And here you have this, I think the reason why you get L0, sorry, the completion in S goes to the one in minus S is because you have this shift. So if you take a look at how to complete one L function, in fact, you get the other one with the minus sign, minus S. No. No, I'm not, yeah, I think even the TSST, I'm not sure there is the statement in the compact case. I think it's special for this, where is it? Non-compact toric threefold. The statement of, if I'm not mistaken, the statement for this TSST is for the non-compact one. But yeah, non-compact toric. Sorry? Oh yeah, I mean, for sigma and sigma star, so the L function, okay, like even more generally, for this mass form, the mass cusp form, in fact, you don't have a character. In this example, it's an artin. Okay, for this function here, you get an artin L function. And, or sometimes, yeah, okay, depends. So this function, this coefficient here doesn't have to be character. They just have to be coefficient of an L function somehow. You need some moderate growth condition for the mass cusp form. No, sorry, could you please repeat the question? Ah, yeah, that's a good question. I think I don't have so far a good, yeah, characterization of what should be. So, okay, maybe like the only hint I have is, for instance, if you take, it's like when you do the functional equation, you completed should have some extra gamma factor. So if I only get one gamma, and then it's not enough to get the divergence series. So in the example, when you have the mass form, typically the way you complete the L function is really uses this gamma S square. Okay, depends also from the spectral parameter. In the cases 1/2, you only have this one. And that's what, in fact, give you a divergence series. But that's my only intuition somehow so far. Ah, okay. I think for this one, yes, I have the Euler product as well. But yeah, more generally, I don't know whether that's the requirement or not. Yeah. Yeah, it's the fact that, okay, so from the topological string side, or somehow from the geometry, what I would consider are the generating functions, so the free energy. Okay, let me just write. Yeah, I will consider in the genus expansion, sorry, in the degree expansion, okay, the genus G Gromov-Witten invariant for X, and then maybe my H bar to the 2 minus 2G. Okay, so these are the Gromov-Witten invariant genus G degree D for X, and this is known to be a quasi modular form for gamma 1,3. In fact, even, okay, I'm a bit writing something not super precise, because, sorry, in fact, what is here I have to put something else. Here I have to put tau, sorry, not this one. Tau, wait, I'm not a bit confused about something. Okay, let me just write tau to the D, maybe it's not exactly the natural coordinate, but the natural coordinate is, so a coordinate in the moduli space, the complex moduli space of the mirror, which is the one at the conifold. Okay, these are known to be quasi-modular form. This is the parameter for which the modular parameter for which you get the quasi-modularity. And conjecturally, once you look at the asymptotic expansion of the spectral trace, this is what you should be able to recover in the large N and large H bar expansion. Now, here we have our F0 and F infinity, which are modular, but in this parameter, okay, Y, which is in a sense related to H bar. So it's a bit different, because you have, okay, you have now H bar is like the free H bar that I was writing somewhere before. This is like the 2 pi Y. Okay, that's the relation. And you have the quantum modularity. So quantum modularity is different from quasi-modularity. The group is the same, but the parameters are also different, because this is a real parameter in the moduli space. that's somehow artificial in a sense. It's not a parameter in the geometry. Although, in the, thanks to the L function that we get, in the L function that we have, it's possible that these are related to Eisenstein series. And quasi-modular form, a basis for quasi-modular form can be expressed in terms of Eisenstein series. So the idea would be, you start here, if you take the, you relate L0 with F, taking the inverse Mellin. Okay, so you have F0, you take as the inverse Mellin of L, and if here you can understand how to write these in terms of Eisenstein series, maybe you can make the bridge. And that's also, maybe I just add the last thing, that could be also natural from the point of view of the TSST, because one of the way you would write the conjecture is that this fermionic spectral trace is kind of a Mellin transform. An inverse Mellin transform, where here you put exponential of the string, the string total gram potential minus mu n, and then you integrate in mu. So that's somehow one of the statements of the TSST. So you see, okay, I'm taking log, here there are exponential. That's the part that contains the Gromov-Witten invariance, even though that's the refined one, but okay, inside, in some limit you can recover the usual, the standard topological string partition function, and okay, yes. So somehow it's not too, and this inverse Mellin is more or less the same expression. Once you change the coordinate, you don't have the exponential, you have the log. So it's a bit naive somehow, but that could be the type of idea that seems to play a role in the story. I think that's in the other limit. I wouldn't say, I guess it depends which limit you take, whether it's the h bar to infinity and to infinity, or rather taking the, I think this fixed, or the other one, which is, okay, n to infinity, but h bar to 0 somehow, and taking the project fixed. I guess it depends on that, because inside that J you have both. You have both the generating function of the Gromov-Witten, and also you have the WKB in the NS limit, which contains, okay, the BPS or the DT. So I guess a priori it's not, I don't think it's just DT. So far, the limit of the DT should be the second one, that gives you here the NS. But again, so far, I'm not even, I work at n fixed and I'm taking the limit in h bar. So that's, I mean, to me so far it's not clear how the same thing behaves when I take the large n limit, because I'm working at n fixed. So I'm not sure whether, like, the Stokes constant, I don't think the Stokes constant we are computing are related to the BPS. Or if they are, it must be some other argument, which is not the way I'm thinking of them so far. So it could be that they are related, but to me it seems, I mean, through this argument, it would be more natural just to relate this with the Gromov-Witten, and that's it. Through the fact that they have this modular property. But I agree that it's a bit tricky, because you have all these parameters, and I mean, even here, okay, like what the mu here is related to the kappa, which is the orbifold. So you have different points in the moduli space, you have this h bar, and okay, you can take this type of limit, but it's not what I think I'm considering, because I work at n fixed. So that's what we are trying somehow to, okay, organize and try to understand in a more clear picture. Thank you.